Hi, so finally managed to get my hands on one of these new Seek thermal imaging cameras. This is the Android version. The iPhone one doesn't appear to be out yet. I think the app has actually appeared in the App Store, but as far as I'm aware they're not actually shipping yet. It's not yet available outside the US officially, and the app is also not available outside. If you go to the Google Play Store to try and download the app, it says it doesn't find it. And if you use a direct link, it says this isn't available. You can actually install it, you just need somebody in the US to download it and extract the APK file. Now I don't know how to do that because I don't really know much about Android, but once you've got that file you can actually install it. It plugged in, installed quite happily pretty much first time. And it's sort of quite a lot smaller than I was expecting. I don't quite know why. It's sort of quite a neat little unit, plugs into the bottom port. There's an issue on some phones, is some phones have the USB the other way up, and the only solution they offer is a lead, which is a bit of an ugly solution. I thought, they could have just offered a version that's got the connection. I don't know sort of how many phones are like that. Having it on the bottom, it's pretty much for a sort of simple thing. It's about the only thing they could have done, but you have to sort of get the hang of holding the phone in a sensible way that you haven't got your hand in front of it. This thing was announced around the time that the Flow 1 started shipping. It's obviously a major competitor. This is $200 and available on Android and iPhones, I think from iPhone 4 onwards. All the iPhones have got Lightning connector, whereas obviously the Flow 1 is iPhone 5 specific, $350. The other noticeable difference is this has an automatic shutter. Particularly when you first turn it on, it clicks away quite frequently, whereas the Flow 1 has the manual shutter for temperature calibration, although I think this mostly uses this for non-uniformity correction rather than temperature calibration. So on the Flow 1, if you're not doing absolute temperature measurements, you can actually just ignore it and not do the manual calibration at all, and it seems to sort of stay working without complaining. Whereas this one, I think it's actually using it sort of more proactively to reduce noise and so on. And this is clearly designed to be, the cheapest thermal image. I mean, say $200 a year ago, you couldn't buy a thermal imaging camera under about $1,000. So yeah, the price has just dropped hugely for entry-level thermal imaging. Now this is a much higher resolution. It's got a 206 by 156 sensor compared to the 80 by 60 the Flow 1. So you'd expect the image detail to be significantly better. It doesn't have the MSX that the Flow 1's got. One reason being that Flow have a patent on that, but also to work it needs the two cameras to be quite close together, and of course if it's trying to make use of the internal camera on a phone, firstly different phones will have the camera in different positions, different cameras will have different fields of view, so it's going to be a bit less useful. Now it does have a sort of fairly simplistic thing where you can actually do a split screen and sort of move the split screen, but what it doesn't appear to have is any way of calibrating the registration, field of view and so on between the two images. Possibly sort of vaguely useful, but not nearly as useful as the Flow MSX, but the higher resolution of the image partly compensates for that. One slight thing, particularly when you're working sort of medium distances, is the camera's obviously quite a long way offset from the screen, so sometimes you're pointing and you don't quite know exactly where it's pointing. You've got some fairly simple temperature modes. You've got spot temperature, you've got auto hotspot detection, and also you can set a threshold so it will just colorise things above a certain temperature. One thing it doesn't do, which is annoying, is it doesn't show you any temperature scale to show you what the range of the image you're looking at is, although the Flow is actually the same in that respect. But most other thermal imaging cameras, it will actually show you a colour scale to tell you what the range is. And in fact this one doesn't actually seem to adjust its range very much. I mean, subjectively the image does look a little slightly noisy. Now the Flow does seem to do quite a lot of averaging and filtering. I think that's probably also reducing noise, but you get quite a sort of quite smooth. This looks noticeably grainier than the Flow image. That may just be because they're doing sort of less filtering on it, but also the other thing that's quite noticeable is the actual range, the colour, effectively the intensity resolution on this. What they seem to have done is actually lock the display range to quite a wide temperature range, and it doesn't seem to sort of change that much. And again, I think that's to make the sensor noise less apparent. If you take something like a soldering iron and put it in the field of view, it doesn't really seem to dim the rest of the field down. It changes a little bit, but it doesn't really auto range as much as you might expect. So I think what they've done is that the minimum span is actually quite wide, just to make the noise look less apparent on the screen. So if you just again compare it with the Flow 1, it does seem to the image seems to have less contrast in it. Although the temperature range of this is supposedly a lot wider. In theory, the FLIR one, they only spec it from 0 to 100 degrees here, whereas this is minus 42 plus 300, I think. I think it's a little bit annoying that, you know, in scenes where you don't have big temperature gradients, yeah, it does look a little bit washed out. There's not much in the way of settings, just colour palettes and a few minor preferences, like whether or not you. One thing is, unlike the FLIR one, you can actually turn off the watermark. You can make it put a Seek thermal logo on it, but you can actually turn that off, which is nice. And you can make it stamp with locations, time and date and so on. And if you do a quick side-by-side comparison with an upgraded E4, obviously the resolution on this is higher, but also you can see the actual, what we're looking at, there's a few mains adapters plugged in. Again, you can see the E4, you've got much more sort of intensity detail, because this is only having running a span of about 12 degrees, so you actually see quite a lot of more sort of black to white contrast. One interesting thing I noticed when playing around with the soldering iron is, although the frame rate is about sort of 8 or 9 frames a second, if you move a target in front of it quickly, you seem to get a group of about 5 images. So I suspect this is probably actually acquiring data at a higher frame rate, and maybe using averaging to now, as regards working range, this sort of stays in focus down to about a foot, and then it sort of starts to defocus fairly quickly. And yeah, as with other cameras, it is possible to use sort of just to improvise an external lens. This is a zinc selenide laser cutter lens. I think it's a 25mm focal length, and you can obviously quite easily make a little cap or something to hold that in place, and that then does actually make it quite usable. So for example, what you're seeing there, that's a couple of SOT23 regulators, so for things like finding shorts on PCBs and so on, it is actually quite usable with an external lens. Obviously, unlike the E4 and also the FLIR one, there's no ability to adjust the lens. The Lepton module on the FLIR one is potentially adjustable, but it's very fiddly. But as a quick sort of add-on eyeglass type thing, that I think all you need is like a little plastic cap or something to put over that to hold it in place, and that would be quite a nice little add-on for doing close-ups, or particularly PCB and component work. Well, I've had this on for a few minutes and it's still clicking away every sort of second or two, so it does seem to be doing quite frequent calibration. There's no obvious sort of there does actually, despite the calibration, there does seem to be a certain amount of sort of fairly fixed noise. I think one of the things they've done, they claim this sensor uses the smallest pixels in the industry, and obviously that's important to get the cost down, to get the die size down. Also, there do appear to be 1 or 2 sort of static pixels just on the edge of the screen. Whether those are actual dead pixels or just glitches or something, I don't know. So I mean, there clearly are some compromises. For a $200 thermal imaging camera, it's not going to perform the same as a $1,000 one, but it is a perfectly usable bit of kit. And at this sort of price, there's really no real excuse for anyone who has any vague need not to have one now, like electricians, etc. The startup time is actually pretty reasonable on this. The FLIR takes about 10 seconds because it's running Linux internally and takes some time to boot up, but this one, plug it in, run the app, and away you go. It does calibrate quite frequently when it's first on, as it's sort of stabilising its temperature. That does slow down a little bit over time, but it still calibrates quite frequently. Now, as well as the camera, you get this little case for it, this little keyring thing in case you want to stick it on a keyring. Feels quite a sort of solid case of the clamp. My main criticism is it's a bit big, really. You've got this tiny little camera and sort of case that's probably sort of 2 or 3 times the volume. Okay, it feels reasonably tough and sort of fairly robust, but just seems a little bit on the big side. But I suppose it sort of does the job. And I mean, certainly for something which you're only going to be using occasionally, it's certainly a lot less bulky than having sort of something this big. So it's certainly something you could just sort of throw, keep in your toolkit for whenever it's needed. It's obviously quite a small lens in here. It is recessed, so although there's no cover or protection, it's actually quite hard. You'd have to really push your finger in there to actually touch it, and the surface is also concave, so it's reasonably well protected against sort of casual finger marking and so on. It's actually a magnesium case, sort of fairly sort of small and light. It feels quite solid and tough. connector feels sort of reasonably solid. Obviously there is a risk, plugging something into the bottom of the phone, if you did give that a knock, it's entirely possible it could break the either the connector on this or the connector on the phone, or both. But that's, the only way to avoid that will be to make it a much more snug fit around the phone. Of course, then the problem is all the phones are different, and if you're using this lot, you might perhaps want to make it like a little screw plug or something to just cushion it to make it a bit more solid. But yeah, certainly for some, most thermal cameras are only going to be used occasionally. I think this is quite a nice solution. It's it's nice and cheap. It's small and reasonably convenient. Now, looks like this thing's glued together. There was actually a mention of glue on one of the Seek Thermal Facebook updates. You can actually see a few slight traces of it. So I'm just going to attempt to just crack it open with a screwdriver. Right, so not a lot in here as you'd expect. The processor, which is an NXP LPC 4320. This is a Cortex M4 chip. Probably the most interesting thing about this, from the point of view of reverse engineering and generally playing with this thing, is that it doesn't have any flash in it. The program memory is stored in an external SPI flash, we can see there, which means hopefully it can be got at, disassembled and played with. Over here is the sensor. Again, we've seen a picture of this on the Seek Thermal published a video of this chip being die bonded to the board. So this is the actual sensor chip here, with the lens assembly which looks like it's glued onto the PCB. Hopefully that lens is attached to to the board and can come out as a whole unit, which would be nice. And there's this shutter unit here. You see the coil on it behind there, and that's just pushed. It looks like it's press fit into the board. So they've sized these holes so this thing just presses in, so it doesn't need soldering. So as expected, not much in here. I'm guessing that's possibly the footprint for the Apple's evil "don't plug anything we don't allow into our phones" chip for the iPhone version. There's some presumably JTAG pads here and a little flex that goes down to the connector. And again, that's something which will probably be different for the two versions. I'll be highly surprised if this board wasn't identical for the iPhone and the Android versions, just with sort of probably that chip fitted and a different flex and different connector arrangement. One issue, obviously, because they're trying to support lots of different phones, is some phones have this connector the other way around. I'm a little bit surprised they didn't have, just make two versions with it. They're going to make a version with this flip the other way around. But pretty much as we expected, sort of fairly simple, minimal hardware. It's interesting to say this is a moderately powerful processor, so I think the original assumption was that they were just streaming raw sensor data out into the phone and doing all the software processing in the phone. But I mean, I think this processor is probably easily powerful enough to be doing most of the processing internally. It may well be that what comes out here is a fairly sort of digestible, usable image. Right, looks like this is just a push fit into the casing. Yeah, this does actually come out. I think just located on some posts. So yeah, we've got the lens assembly attached to the PCB, so that's good. This looks like this has been hotbar soldered down to the board. Which one is this? Yeah, this is probably just another post fit into the case. So that's the coil for the shutter. It's a little rubber sort of grommet-y thing here. Again, that looks like the lens element. I believe this is a chalcogenide lens, similar to the Fleury 4, glued in. Obviously there's no real scope for adjusting and tweaking the distance on this as it stands. You'd have to look at the problem is also the alignment. This is probably aligned in some sort of jig and then glued in place once the alignment's right, so as soon as this comes off the board your lens alignment's probably going to be screwed, unless it comes off cleanly at the glue and you can actually seat it back in the hole in the glue. Also the height of this might make it a bit fiddly to use an external lens, depending on, if your lens had to sit closer than here, then this could get in the way a little bit, which would be a bit of a pain. But if you had a lens that was sat further up here, then you might be able to use an external lens with it. See in here there's a sort of plastic rotor with a couple of magnets on it, so that's going to be moved by the magnetic field from that coil to flip this shutter. And this looks like it's powered to sort of move it up. I'm guessing there's maybe a hole in it, because I wouldn't expect it to be in a situation where it needed power to actually be open. So I'm guessing there's probably a hole in that vane. So that's the straight through, and then that's the calibration position when it lifts it up. Let's take the shutter out, and actually surprisingly it does actually by default sit in the closed position, and it needs sort of current to keep it open, but it's only a couple of milliamps, so it's not a huge deal. But so it means this is actually continuously drawing current just to keep the shutter open, but say about a milliamp or so, it's not going to cause a major issue. And you can see these pins are specifically designed to be press fit. They've got this sort of hole in the middle so that they actively spring against the side of the hole. This is a sort of fairly common technique. You can buy Samtexcel pin headers with these, for example, so you can just press fit them into the PCB instead of soldering them. Well, with the shutter out of the way, we get a slightly better view of the sensor. It's quite sort of thick, and the construction looks quite similar to what we saw in the E4, sort of layers of sort of silicon or similar materials. So that will have the sort of vacuum cavity in there, and probably some electronics built in. Obviously, there's no other obvious electronics on there, so it's sort of fairly thick. It's about, I estimate, about nearly 3 millimeters thick. And it looks like it's a stack of a few different layers, but these are obviously manufactured on one sort of big die and then sliced up afterwards. Can't quite see, but it's die bonded directly to the PCB, so I don't want to take this lens off for the moment. With the shutter out of the way, you can just about see the bond wires. Rough count, there's something around 15, somewhere between 15 and 20 bond wires. I've just hooked up a little cable onto this just to make it a bit easier to play around with. Just while I was at it, just check the power consumption. It's about 53 milliamps, which is sort of not too unreasonable. I mean, that's obviously the 5 volt supply. Obviously the Flow one has that separate battery. That's got a sort of fairly powerful processor in there. I don't recall what the actual power draw on that was, but I think it was quite a lot more than 53 milliamps. This doesn't seem to have a switch mode regulator in it. I'm guessing most of the rail is probably a 3.3. I'll have a poke around to see what voltages are there, so they could have made this slightly more power efficient using a switching reg, but I mean 53 milliamps isn't really a great deal on a sort of phone size battery, so it's not really worth worrying about, I don't think. I've removed the shutter, so the image is going a bit loopy because it's thinking it's trying to calibrate, so and not doing so you get all sorts of weird ghost images. So for example there we go. You don't actually see any indication on the screen, so it's obviously just done a calibration there because the screen just gone nuts. If I stick my hand in there, you now see the ghost image of the light. Now it's calibrated again against my hand, and again it will just go generally fairly nuts because it's calibrating against what it thinks is a flat image, but actually isn't. Take a close-up look at this board. Not really a lot on it, as you'd expect for a minimum cost product. I don't really know how many layers. It's definitely at least 4 layer, could be 6. Now obviously it's a low-cost product, but the PCB is so small that the cost of the PCB is going to be minimal, even if it has to be a 6 layer. So on this side we've got the flex from the USB connector. We've got the flash that holds the firmware, a few passives there, and the sensor. And on this side, again not a huge amount, there's this, which I'm guessing is the Apple Evil chip for the Apple version. That I'm guessing is going to be the voltage regulator that takes the 5 volt USB supply down to 3.3 volts. This processor's got an on-chip core voltage regulator. Doesn't seem to be any other sign of voltage regulation for the sensor. It's possible that might be a regulator, but there's not really much else. There's this block of 4 resistors, and each of these goes to a test pad, so I'm guessing that's going to be the main interface, which is probably going to be something like SPI. You can also see that the ground plane is split between the two. Now that might be to avoid this coupling noise into the sensor. Might conceivably be for a little bit of thermal decoupling as well, to avoid getting a temperature gradient across the sensor. but I would have thought, yeah, the tiny little thin copper layer compared to the thickness of the PCB wouldn't make a huge amount of difference in that respect. There's these 4 test points, there's a few other test points, and obviously there's this group here, and this is going to be, I'm not totally familiar with this chip, I'll have to look it up, whether it's JTAG or direct connections to this flash. I don't know if this has got a mechanism for programming the external flash via the debug port or not. It may well have. I'll have a look through that a bit later. And then there's this, which I'm guessing might be something to do with the USB, could even just be a protection diode array or something for the USB. And there's this little crystal oscillator. Actually, there's 2 caps there, so I'm guessing it's probably a crystal rather than an oscillator, and that's pretty much it. So I think it's time to start probing around this thing with a scope. Well, you'll notice these, there's a load of rectangular pads here, there and there, and I'm guessing that may be to provide the option for a shielding can over this for EMC, which obviously wasn't required because it's not fitted. Although it's in a metal case, actually getting a good low inductance connection to the case can be quite difficult, so if it needs shielding, then actually shielding it on the PCB is probably an easier and cheaper and more effective way of doing it. But I've tested these, and these are all connected to ground, so just the fact that the pads are that shape would suggest that they're for just the tabs of a little shielding can. So a few surprises from some initial probing. It does actually have a switching regulator. This is a switching regulator. I didn't spot it because that's the inductor. It looks a little bit like a capacitor, except it's a bit darker in colour. That's producing a 2.8 volt logic supply for the processor. This other chip here also looks like another 2.8 volt regulator, so this is probably a linear regulator producing clean supplies for the sensor. And the biggest surprise is that there's no AC signals at all on any of these test points. And in fact, if you look at this more closely, this resistor pack is actually being fed from the output of this regulator, and then it's going, for example, this one here you can see goes through probably an inductor or a ferrite bead and a capacitor. So these are actually separate supply rails for the sensor, so you've probably got like an IO voltage, a core voltage, maybe some analog supplies on there, but there's no AC signals anywhere at all on this this side of the board around the sensor. So I've scraped some of the solder resist off the bottom side, and so far I've found there's a sync pulse here which is running at about 32 Hz, which might support the theory that it's actually running at a higher frame rate and then downsampling on the processor. And there's a 60 MHz clock, and there's another signal that looks like a data line, so I'm just going to solder some wires onto these so I can look at these in more detail. Right, I managed to find some signals that look like they're the data signals from the sensor, and eventually managed to get some wires on. In all cases I just scrape some resist off and solder onto a via. And this signal down here is a sync signal. This is the pulse that's running at 32 Hz. I don't know if that's a sync out, like a trigger out to the sensor, or a sync back. If I wanted to find out, the way I could do it is if I cut that track and put a resistor across it, I can then sort of put a load either side and see which one moves under the load, so that'll tell me which side was driving it. But obviously it's a bit of a fiddle with tracks this fine, so I'm not going to bother doing that for the moment. I haven't really got time to do a serious investigation into this at this stage. Then we've got these 2 vias here. Fortunately these come out the other side, they're a bit more easy to get out the other side, but these, there's a 60 MHz clock on this track here, and then there's 2 sort of signals here that look like sort of data related, which we'll take a look at. Right, so these are the signals I've found. This top one is that sync signal. That's happening at the rate of 31 milliseconds. Then we've got these other 2 signals here. Now, interesting, this top one, a couple of things here. One is that during this pulse we see this appears to be tristating, so I wonder if that's maybe a reset out to the centre and it's actually tristating its output. I suppose it could also be a chip select, and like an SPI type style chip select, so we've got like this is actually sort of selecting the chip, and it's when it's not selected we've got this tristating going on here. But what's interesting is all this data seems to be fixed. I can't see anything changing at all on it. It seems to be sort of fairly sort of arbitrary data, but pretty much wherever you look, yeah, it's not changing at all with the data. So I'm not quite sure what's going on there. This second one is moving around, and the first thing we see, we've got a binary count here, so this is clearly a sort of frame number of some sort. And looks like we've got some other odd little bits of data. And then we've got what looks sort of like it's almost certainly image data. We've got sort of some noise floating around. One thing I did notice is that some of this doesn't change when you wave your hand over it, and some does. So I'm guessing there's maybe some reference data, sort of maybe some covered pixels providing some reference data. If I should wave this holding iron in front of it, we see a very sort of rapid change of that. It's clearly image data. And I think that looks like it's probably binary, so if we can find the boundaries on that. Yeah, so I think that's probably the framing. So we've got all the least significant bits here. And as I put the soldering iron into the field of view, you can see this sort of clearly, we've got a binary count going up with sort of the lower bits here, the more significant bits at this end. So it's heating up now and cooling down. Yeah, it looks like we've got 14 bits of data. I haven't found a clock, any obvious clock for this. It could be using the 60 MHz clock, or there might be another signal buried on it in a layer or something. So look at the data rate. This is about 15 MHz, so that's a quarter of the 60 MHz incoming clock. I'm really puzzled by this fixed pattern data. It does seem to be an issue. I tried shorting that line to ground and it did sort of freeze the image, so it does seem to be used. It'd be quite interesting to look at the direction of this, but it's going to involve some fairly intricate track hacking, which I don't really have time to do at the moment. It's interesting also how this data is sort of in bursts, whereas the rest of the data seems to be fairly consistent. Yeah, all these seem to be data packets. Right, there's 156 of these per frame, so that's clearly the horizontal resolution. And if we divide this up, we get about 206 14-bit words, so that obviously corresponds to the horizontal. So this is clearly our horizontal data in what looks like sort of vaguely binary format. I've not looked into too much detail, but it does seem to be doing a fairly consistent count pattern. But say what is interesting is, this is coming in at a rate of sort of 32 frames per second. So obviously it'd be quite hard to actually get at that, and also the other issue is that's probably going to be quite noisy data. So if you did actually want to try and get at this data and use it, you'd almost certainly need to put a bigger lens on it to make it usable. But yeah, so I'll leave it for now, because that is potentially accessible and you could potentially run your own code on it. I've got another couple of these on order, so as and when they arrive I think I might sacrifice one and do a full sort of strip down, take the chip off and trace all the connections out, because it probably wouldn't be that difficult to sort of run some code. Obviously there's also, because the code's held in that external chip, and I believe there's also a firmware file as part of the install package, you could probably get some useful information by disassembling that, which might at least give you some clue as to which data is coming in and out, and maybe sort of some idea as to the meaning of this stuff here. So if you want to hook this thing up, it's a lot less straightforward than the module in the FLIR 1. But because it's got this USB interface, it may well be relatively easy to hook it up to something like a Raspberry Pi. There's some guys over in the thread at the EEV blog forum who've done some initial sort of USB traces, and the data format over USB does look to be fairly simple and fairly identifiable. So at least sort of using this as a USB camera for a device that does support USB host, like maybe BeagleBone or Raspberry Pi, may actually be relatively straightforward to do. But as regards sort of getting the raw data out the sensor, if nothing else, just physically getting at the pins is going to be quite tricky. But I think the way to go on that is probably going to be to actually load new code into the processor and pull it out that way and spit it out of some more accessible pins somehow.